We're about to start our day 3 of the symposium and the summer school. And Kilian is going to continue his 3-lecture series. The first lecture was amazing. I'm anticipating another really engaging and fun lecture. I recommend everybody to continue to engage with Kilian through the chat stream. And the floor is yours, Kilian.
Good morning, everybody. So yesterday we talked about a bunch of things, and essentially we talked about machine learning in the very the very simplest way of machine learning is essentially a linear classifier, right? So it's basically the following. So we have some data that's given to us. Let's say we have some positive points and some negative points. These are kind of nods and crosses. And so we want to have a function that allows us, when a new point comes in, to tell us is it positive or is it negative. So these points here are called the training data, right? So these actually, we know these are positive and these are negative here, right? And we would like to know a function for a new point. Maybe this here is my mystery point. Is this positive? Is it negative? And the way these linear classifiers do it is they essentially learn a hyperplane, right? And this hyperplane is parameterized by a vector W and an offset B. And the offset B basically just says, where are you along this hyperplane? And for those who know the equation, the hyperplane is defined by this equals 0. So all the points that satisfy this constraint are on the hyperplane. And for a new test point, I can basically now, so basically what I do is during my training time, I take the data that I know, I place the hyperplane such that the positive points are on the, for the positive point, we have W transpose X plus B is greater than 0. For the negative point, we have W transpose X plus B is less than 0. And then when a new point comes in, I just plug this into this equation. And if it's greater than 0, then I say, aha, this is a positive point. If it's less than 0, then I say, aha, this is a negative point, right? So this is kind of what we do during test time. And this was the first algorithm of this kind was the perceptron, which was invented by Frank Rosenblatt in 1959. And so I introduced the logistic regression classifier, which basically, was just a way, it's basically just a way to learn this hyperplane. And it gave a very specific probabilistic interpretation of this hyperplane, which basically said, okay, I'm defining a function that says the probability for a point to be positive is 1 over 1 plus e to the minus W transpose X plus B. That's our, this is just a modeling assumption we are making. And we call this is the sigmoid function of W transpose X plus B. So we don't just have a hyperplane. We don't just say, oh, are you positive? Are you negative? We're also giving you a probability, right? And this is the sigmoid function. For those who kind of remember it, the sigmoid function looks like this. This goes from 0 to 1. And here's 0.5. And so the way you have to imagine this is basically that the sigmoid function is kind of orthogonal. It's along this vector W. And here you're basically squarely in the 0 region. Here you're squarely in the 1 region. So when a point lies here, right in the middle, right in the hyperplane, then I'm here, then I say, well, it's 50-50. I don't know if it's positive or negative. I have no idea. It's right on the hyperplane. And if a point is here, then basically I move over here and say, okay, it's positive. It's here, I'm going negative, right? So essentially, I'm just learning a line on which I project the data. And I say, if you're further in this direction, you're positive. Further in this direction, you're negative. That's all there is to it. And we went a little bit through some math and said, okay, well, if I want to optimize this, if I now want to, assuming I take I take this modeling assumption, now, I want to learn my parameters W. I want to position this hyperplane, and how do I do this? I do minimize the negative log likelihood of the data, and this gave us the following loss function, which said we go over all our data points, and we get the following function log of 1 plus e to the minus W transpose Xi plus B. I'll just make this prettier. No one can read it. W transpose Xi plus B times Yi. And then we go. So this here is, maybe I make this a capital loss. And this here is the loss of the individual point. This is the loss, we can call this of W transpose Xi. plus b and yi. Okay, so this is our loss function. We're trying to minimize this function. And machine learning is always like this, essentially, right? You're basically defining a loss function, which tells you, in physics, you can think about it as an energy function, right? You want to minimize energy, right? So here you're basically saying, okay, a loss function that tells me how bad am I. Typically, you define the loss function that is always positive. That's the case here because you have a log of something 1 plus something positive. So this is always greater equals 0, right? And basically, when every point is classified correctly and really far off the hyperplanes, then what we get this here is essentially 0. We get log of 1, so we get 0, right? So basically, the loss higher means, okay, some points are a little bit too close to the hyperplane for comfort. Maybe we should position the hyperplane a little bit, or make W a little larger. Or that, maybe they're even on the wrong side, which would be bad. But if the loss goes down, that means we're making fewer and fewer mistakes. Okay. Any questions at this point? This was just recap. Let me talk about one more thing. In machine learning, classification is just one setting. There's also other prominent settings. A typical one is actually regression. So I didn't talk about regression last time. It's basically the following. Let's say we have data points here, and you would like to find a hyperplane, a line, a direction, which, actually, there's no arrow here, which explains your data, right? And so, ordinary least squares, that's exactly the same thing, and you can just have different loss functions. So for example, one loss function we could have is the following. It's 1 to n w transpose xi plus b minus yi squared, right? So this here is just the, essentially what I'm doing here is I'm saying, okay, I try to find the hyperplane, and I'm penalizing how far off every data point is from the corresponding point on this direction, on this direction that I'm learning. Does that make sense? Thumbs up if that makes sense. Wait, I'm not seeing. Okay, good, terrific, right? So regression classification, all the same thing. In this case, basically, you could go through exactly the same motion in linear regression. And also, essentially what you're doing is you're saying, okay, I'm defining the probability of a data point, of a label of a data point given x, is just, you have a Gaussian, is proportional to a Gaussian of w transpose x plus b with some variance. And then you do log likelihood to fit this w. So you do exactly the same thing we did last time in the lecture. And what will come out actually is ordinary least squares. So let me just remove this here. 1 second. Okay, good. Then the L is a function of B2, right? That's exactly, oh, yes, good point. The L is a function of B2. You're totally right. The reason I forget the B is because often in practice, what people do is they just say we map X to X and we add a little 1 in here. And then you can actually absorb, you say B, the new B becomes, the new vector W becomes W, and you kind of attach the B as one more dimension. And then if I have this new, let's call this here W bar and this here X bar, then W bar transpose X bar is the same thing as the X transpose W plus B. So you can actually absorb the B completely in the vector W. So in practice, we forget about this B. Make sense? Thumbs up? Yep, okay, good, terrific. All right, then we talked about two more things, that's kind of important. We made this assumption, right? This assumption was that, well, we can find a linear function. We can find a hyperplane that separates the positive and the negative points. How restrictive is this assumption, right? In practice, right, it seems like a crazy coincidence that you can really put a hyperplane between the positive and the negative points, right? And, well, turns out, let's say my X is element of RD, just to introduce some notation. If D is very, very large, then actually this is not an issue, right? If D is very, very large, then, there's always some way of wedging a hyperplane between data points, between these data points. In fact, you have the opposite problem. will always find it, but maybe you will actually, use some features that are not very interesting. So for example, let me just explain this. So let's say, last time I talked about neuroscientists. So let's say we have fMRI images of people with Alzheimer's and people without Alzheimer's. We know that not every part of the brain is affected by Alzheimer's, right? Or actually, maybe you do something, people with autism or people without autism or something, right? And so you may have an hypothesis that only a small part of the brain may be affected by this, right? If your classifier uses all the information, it's cheating, right? It's pulling out something that's just a spurious correlation between the affected, the positive patients and the negative patients. And this can't be the right answer. And so what we did there is we said, okay, this is at the very end of the lecture, we said, okay, we minimize W subject to the constraint that, we basically add a regularizer. We basically say we minimize the loss. Here we basically say, try to make as few mistakes as possible, but we also penalize the norm of W. And so if this is the L1 norm, this is called lasso or L1 regularization. And essentially what this lasso does, it basically says, you have to pay, right? If you increase the weight of any one of the features, you have to pay for it, right? And so this is lowest if everything is just zero. If you're basically saying, I'm disregarding a feature. And so essentially what you're forcing the algorithm to do is to learn the features that it itself needs for classification. Here's the other setting. If D is small, right? So maybe D is greater than 0, but not much greater than 0, right? So you only have like 10 dimensions or something. Then this actually is restricted, right? Then the fact that we actually can only learn a linear hyperplane is a problem. And what I talked about last time is, let's say, okay, we go from X to phi of X. So instead of actually learning the classifier, basically, our classifier, let's call this H of X, is W transpose phi of X plus B, right? And phi of X can be some mapping from, for example, X to, X1 to X2 to something X1, X2, X1 times X2, X1 squared plus X2 squared, etc. Right? So you basically add some nonlinear interactions between these features, and this allows you to learn some nonlinear hyperplanes. So nonlinear decision boundaries. So for example, I had this case here. Let's say, my positive points are in the middle in the circle, right? Here, this guy actually, this dimension says how far are you from the origin. So actually, if you cut linearly off, then you actually learn a circle, right? So actually a linear hyperplane in this space, in this new space, translates to a circle in this space, right? So that's great. So basically, if our dimensionality is too small, if this assumption that we have a linear hyperplane is too restrictive, we just take our features and map them into a high dimensional feature space and some more nonlinear feature space. Now I know what you're thinking. You're going, well, in this case, this works out really nicely because you knew the answer, right? You knew that basically, in this case, this feature here is the solution, right? It's really, really good. But what if I don't know the solution? And that's exactly what Frank Rosenblatt thought about. And he got a lot of criticism. Like when he introduced the perceptron, initially people were really, really excited. And then they realized, wait, this is just a linear classifier. Right? And I mentioned this last time. People came up with this XOR problem where they basically said, well, what if I have positive points here and negative points here? You can't learn this, right? If you can't learn this, what can you learn? This is no good. You suck, right? And so he came up with a new solution that was called the multi-layer perceptron. Multi-layer perceptron. Also often referred to as neural network. Neural network. But nowadays, deep net. All the same thing. Okay, and what's the idea? The idea in that neural network is the following. Let's say, we have a data set, and let's say we do regression. So our loss function is just the square loss. And, this is our data set, right? And so, well, we can just see here, right? A line is not good, right? If you approximate this with a line, it's not going to cut it, right? What we really want is a kind of non-linear function, right? Okay, good. So we already know the trick is to kind of map our data from X to some feature space phi of X. And then we basically learn our classifier H of X equals W transpose phi of X plus B. So basically what we are hoping is that we can transfer our data into some space in which this curve here is actually a linear, it's actually a line, right? And so maybe there's some kind of clever combination of these features that allows us to do this. Okay, quick check. Everybody still with me? Thumbs up, thumbs down. Any questions? Okay, awesome. Good, good, good. Terrific. So if you had a clever way of coming up with this, right, you can do it, like you could come up with these features. But what Frank Rosenblatt is saying is actually, I have a really good idea, right? I came up with this perceptron, right? So why don't we just say our mapping phi goes from X to the output of a whole bunch of perceptrons, right? Fm of X. Right? Where each Fk of X, or we can choose a logistic regression classifier, the same thing, where each Fk of X is itself the output of some, let's call this U, transpose X plus Ck, right? And this here is again just our sigmoid. So the way you can think about this is essentially we are learning a bunch of classifiers, right? And we stick the output of these classifiers into the perceptron, so into the final linear classifier. So the intuition is a little bit, you basically learn, kind of divide it up into a bunch of regions, right? And these classifiers kind of divide this up, and then basically in each region you kind of learn their own little function. Now I will get to this in a minute. I will kind of solidify this in a minute. Okay, so basically saying, well, it's kind of like these Russian dolls where inside you open them up and inside the Russian doll is another Russian doll, right? That's essentially what he's doing. He's like, well, my perceptron is not good enough. Well, let's just stick a lot of perceptrons inside my perceptron, right? And if that's not good enough, we stick more perceptrons into my perceptron, right? So the answer is always just no more perceptrons. So that's the idea. You have our X, we just learn a classifier, we learn a bunch of classifiers, right? And we don't know what they're predicting. They're predicting something, right? And then we stick the output of these classifiers again into a classifier. So, and if you draw this, right, then the way people drew this is was following, and now you can see why it's called a neural network. This here's my X, this is my X1, X2, these are my different dimensions. And what you're saying is, well, here's my F1 of X, takes as input all these different, takes all the dimensions of my input. Well, so let me just make this a little cleaner. Okay, now I have my F2 of X. Again, takes all these guys as my inputs. I have my F3 of X, and so on. Let's say I only have a three-dimensional representation here. And then I have my H of X, which takes these as input. And so now it looks a lot like something like a network, right? But really, it's really, really simple, right? It's really just saying, okay, we have a linear classifier, a linear classifier, a linear classifier. They all give me outputs, and I stick that into a linear classifier. Quick question, any questions? Thumbs up, thumbs down? Everybody with me? Okay, good. All right, awesome. Good stuff. And so the final loss is then, I'm basically minimizing. I'm minimizing my my loss function over all my data points, but this time actually with the output of this final H classifier, comma yi. Right. So and this can just be the logistic loss or something. This can be just the loss as before, right? And when I'm do learning, and I will get to this in a minute. Then I just compute the gradient with respect to the parameters of each one of these functions, right? And this. So each one of these is parameters. I can just take the gradient with respect to each of them and just do an update, right? Last time we talked about how we learn these functions with gradient descent. We can do the same thing here. It's really not a big deal. Okay, let me just write this down a little bit so that you just that maybe becomes a little clearer. So we have this function h, which is just a linear function, right? And each one is a linear function of this representation phi of x. And this phi of x basically is each dimension is defined as something like this. I can now just take these guys and stick them together, right? And kind of write them as one equation. And so basically what I get is, maybe I can use another, I just realized I can use all these cool colors. Here, h of x equals w transpose, right? And it's phi of x. What's phi of x? Well, it's really just, sigmoid of u of x plus c. And what's u here? U is just a huge matrix where each entry, each row is one of these u vectors. Okay, so let me just explain this. So here fk just does uk of x plus c, right? And so essentially what I'm doing is I'm just multiplying x by this uk, right? But every single k is every single f is structured the same way. So what I can do is I can just multiply x by a huge matrix where each row basically is one of these u vectors. Then I add my c vector to it. That's just, from c1 to cm. And then I apply the sigmoid, to this nonlinear transition function to every single entry. So this here is a vector, which is the output of all of these guys. And then I apply my sigmoid to it, and I multiply with w. One more time, check. Questions? Thumbs up, thumbs down? Okay, well, actually, yeah, 4. Okay, maybe I can write it one more time as a sum. So if I write this, can I? Yeah, well, let me just write it here. So what we get is h of x equals the sum over k, wk sigmoid of uk transpose x plus ck plus b, right? And so what I did is I just plugged in this here in here, right? And so this w transpose, this representation is just w1 times f1, which is this, right? And so basically I'm summing over all the weights of the outer linear classifier times the representation that I learned by the first hidden, this hidden unit. And at the end, I just have my offset b. Okay, so, and this is actually, all there is to it, to a neural network. It's I'm sure you've heard a lot about it. There's like movies, Terminator and so on, right? Of neural networks taking over and all this stuff, right? But it's really actually very, very simple. It's just a simple function, right? It's basically just, a composite function of a bunch of linear classifiers. So why is this so powerful, right? And let's just think about this for a second. What is this function in here, right? What is this, right? This here is a linear function, and the sigmoid, right, basically has this shape, right? So if you just think about it, if you just do this in 1D, right, then each function, each of these functions fk has the following shape. It basically says, well, I have, some sorry, let me just 1 second. So, yeah. So this essentially tells you the sigmoid basically, goes like this, right? CK basically shifts this to the right. So if I basically make CK very, very negative, then I need more energy to go to the, I can basically look like this or this. This here makes it flatter or not. So I can make it like this, or I can make it like this, right? So if U is very, very large, then it kind of looks like this, right? And if it's negative, then it looks like this. Okay, so it basically kind of looks the other way around. So, and what does W do? W can actually make this function and make it wider, right? So if I actually have a sigmoid that's between 0 and 1, and I multiply with a large number, then it goes really, really high, right? If I multiply with a small number, it goes like this. And if I multiply with a negative number, then the function looks like this, okay? So one more time. C here is the horizontal offset. This here is the steepness. And this here is basically the how wide it is, right? Offset and steepness. And that's what I'm learning. So, oh, wait, there's some questions. Is sigmoid function? Oh, sorry, I didn't see these functions questions earlier. First question, in the loss function xi stands for the data sample and the net x is a component of 1. Yes, sorry about this. So here you're right, that is actually unfortunate notation. So here I meant the kth dimension of x, and in the loss function I'm actually summing over the ith sample. Yes, I agree, it's not ideal notation. Thanks for pointing this out, Marjan. Question by someone from is sigmoid function is applied to each element of the matrix, or are we calculating, for example, exponential of matrices in the sigmoid function? Ah, very good point. So when we do this here is actually a vector. X is actually a matrix times a vector, right? Plus a vector. So this here is a vector, and this applies the sigmoid to every single entry. So every single entry basically is just one of these functions, right? So the output of this is basically exactly this. So each entry basically is one of these functions. Okay, he says, is this the so-called Kolmogorov-Arnold's theorem? I don't know. I have to look that up. I don't know. It could be. There's a lot of Kolmogorov's theorems. Okay, good. Any more questions? These are great questions, guys. Okay, good. All right, let's go back here. So we basically, so what is this function h, right? It basically is a weighted sum of a bunch of these sigmoidal functions. And so let's think about this for a second. Let's say we have a bunch of these functions. So we have the first one that maybe looks like this, right? The second one that, who knows, looks like this. And the third one maybe looks like this, right? And now what is h? H is the sum of these guys, right? So what do we get as our h? Is that initially it's like this, then we go up here, right? Then we add in the red guy, and then we add in the green guy, and this is the final function, all right? And so what you're realizing is, what a neural network is doing is really just learning these piecewise linear functions, right? So the sigmoidal units, what they're really doing is these classifiers, they're telling you at what point am I going to add a new piecewise linear function to it. And if I now go, imagine you have a data set, the example that we had earlier, out of something like this, right? So what does the neural network learn, right? It basically learns something like a step function, right? It basically goes up like this, and then goes down, and goes down, right? and that's really all there is to it, right? And the key is that if you have enough of these if you have enough of these components, you can approximate any function arbitrarily well, right? You just need more of these piecewise linear functions, right? No matter how complex your function is, right? You can approximate anything, right, with a lot of lines, okay? I see. Okay, and so essentially, essentially that's really all there is to it. In practice, actually, people rarely use the sigmoidal unit as these interim functions, and the reason is very simple: that you have a lot of these flat regions, and these flat regions are a little hard to optimize because you have no gradient there. And so if you take gradient descent, it's tricky. So what people do instead is they define a different what we call transition function. So nowadays, what's all the rage is a rectified linear unit. Rectified linear unit. You basically say sigma of z equals max z comma 0. So these functions, they look a little different. They don't look like this. Instead, they look like this. And they actually have a line here. And once again, same thing, right? You learn a bunch of parameters, and so you can actually then learn functions that go like this, or go like this, or a steeper, or a less steep, and so on. And so the function that you're then learning is a whole bunch of piecewise linear functions, but they're all actually, you know, they're not always so flat. That's basically the main point. So in practice, it's easier to optimize this guy. Question. This makes sense for a regression problem with continuous values of y, but how do we formulate this as a classification problem with discrete labels? Very good question. And the answer is very simple, right? If you actually want to have a classifier at the end, then we just say h of x equals sum of a k, wk, sigmoid, blah, 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 all this stuff, right? The same thing as before. And what do? We do one more sigmoid around it. And now we actually have a binary classifier. And so why does this make sense? So essentially what we are now learning is a hyperplane. Let's say we have some data points here, positive and negatives. And so, you know, think of it as the following. You're basically now learning a regression function, right? It's the same thing, but that separates the positive from the negative, right? So what you're learning actually is this hyperplane, right? And so this sigmoid here just tells you, don't try to approximate this function. Instead, actually make that the positive points are on one side and the negative points are on the other side. So actually, you know, classification and regression is really the same thing. It's just that in classification, you learn a line that's a hyperplane, or no, it's not really a hyperplane, it's a surface that separates the two data points. In regression, you learn a surface that explains your data points, right? And the only difference is this sigmoid out here. Where this here actually in this case is is the real real sigmoidal, not the rectified linear unit. Benjamin, does that answer your question? Okay, awesome. Srikar, do you encounter any issues with differentiability at the kink of that function? Yes, good point. We will get to this. Very good point. So what Srikar immediately spotted is, wait a second, this is not differentiable, right? You're talking about taking the gradient the whole time. This function here is not differentiable. Now, who cares? That's just one point where it's not differentiable. Actually, it's a big deal, right? Because the gradient will always point exactly towards this one point where it's not differentiable. It turns out in practice, it's not a big problem. And I will get to this. And if I don't get to it, please remind me. In a minute, I will tell you how we actually optimize this. Very good question, though. You can, of course, square it, and then actually it's differentiable. So that's another cop-out. Any other questions? Okay, good. If everybody's good, then let me just go to 1 second. So you now know what a neural network looks like. It's basically we have our X, right? And so here are my different dimensions. And basically what I'm learning, a whole bunch of classifiers that take these as input, right? And each one of them takes, and then I basically have my output. And this is called a neural network with one hidden layer. right? So that you basically see the output, the input is clear, the output is clear, and the hidden layer is inside the neural network, and it learns something, right? And you don't really know what exactly it learns. It doesn't really matter, right? It learns these different components. And so here comes the interesting thing. So neural networks were actually very, very popular in the 1990s. And most of machine learning was occupied with learning neural networks. And then they became out of fashion. And why did they come out of fashion? And there's actually two reasons for it. And one is actually a theoretical result that basically showed that one hidden layer is enough. So if you have one hidden layer, if you just make it wide enough, you can approximate any function. You can call this a universal approximator. And that makes sense, right? If you think about it, you basically, no matter how complex your function is that you're trying to learn, right? You're approximating this with a whole bunch of piecewise linear functions. But if I just have enough pieces, right? It can, you know, in the limit, I can actually approximate this arbitrarily well, right? So it's not a big surprise, right? And it works really, really, you know, works really well. So not a big deal. But so because of this, everybody only looked at these one layer, you know, neural networks. And last time someone mentioned support vector machines, then people came out and said, well, what you could do instead is you could actually not learn this, you could actually specify this. And the problem is it's kind of a pain to learn this. So actually neural networks kind of fell out of fashion. And in the last 10 years, what happened is that neural networks became again very, very popular, and through deep learning. And so what is deep learning? And deep learning is something that actually Frank Rosenblatt invented, you know, already in his original paper. And he said, well, you don't need to have one hidden layer. You can actually have more hidden layers, right? You could actually have another set of hidden layers, right? Where each one here takes an output, these guys. And then you can have another one, right? And so on. You can have as many as you want, right? And then you predict your output. And that's called a deep net. So a deep net is the same thing as a neural network, just means you have more than one hidden layer. And the reason people call it deep actually is actually a joke. So Jeff Hinton and Jan LeCun did this, and they started using this terminology. And the only reason they did this is because at the time it was very, very popular just to have one hidden layer. And you know, they basically called the other ones deep. And the only reason they did this is so that everything that's not deep is called shallow, and they want to call their colleagues shallow. So that was the joke. That's where it came from. But they, you know, it became very, very popular. And so when you think about it, each of these layers essentially just takes X, and then you basically multiply this with a matrix, right? You just go, well, this is W transpose X, right? And this is phi, right? And then this is phi prime equals U transpose phi, right? And then we have phi double prime equals whatever, V transpose phi double prime, and so on. So you just have a bunch of, you know, matrix transformations here. And then always, you know, the other thing is you always apply some nonlinear transition function around it. So some sigmoid. And this is all there is to it. And what happened in the last couple of years is that these operations here, matrix multiplication, became really, really fast because of GPUs. And the other thing we realized is that actually one hidden layer is true. One hidden layer you can approximate as much as you want. So it's always sufficient to have one hidden layer. But actually, if you have more hidden layers, then actually, essentially what you're doing is you're reusing parts of your function. So basically, the number of kinks you have grows exponentially, actually, right? So if you think about it, each one of these points, right, is a function. It's something like this, right? So the wider my network is here, the more kinks I have. Okay, so you know, the more piecewise linear functions I have to approximate my function. If I now have one of these, this actually uses all of the kinks that these guys has, right? And so essentially what I can do is I can actually, and if I use this one, it uses all of the kinks of this guy, but each one of these uses all of the kinks of this guy. So actually what you do by each layers, you actually get all the kinks of the previous layers multiplied with each other. So the number of piecewise linear components that you have grows exponentially with depth. That's the point. So you don't actually need that many parameters to learn a really, really complicated function. That's the advantage. So essentially, by having deeper networks, you can learn really complicated functions relatively quickly. Sorry, I missed it, but what makes each perceptron in the layer different? It seems like they all have the same, take the same input data. Oh, very good question. So basically, what they're saying is, well, these guys, right, why are they different? And there's a very, very good point. I didn't get to this. So here comes a very important part of this. And this is why people didn't like it as much as first. I remember last time I said the logistic function is the convex function, right? So basically, when you learn logistic regression, you're minimizing a convex function. So you start somewhere here, it doesn't matter. You just set W's on random vector and you get to the minimum. This is not the case for a neural network, right? So the moment you learn all these various parameters of all these different functions, right? This function looks like this, right? It looks nothing like a convex function anymore. And so what happens is each one of these weight vectors you initialize randomly, and they all learn very different. Because you initialize them differently, they actually end up at different solutions. And actually, the whole network, what you learn depends on the initialization. But if you basically randomly initialize all these vectors and you learn something, you and I both randomly initialize and we learn that to train the neural network, we actually get different networks at the end. It's not a convex problem. Srika, does that answer your question? So it's a very good point. So all of these guys are initialized randomly. And this is actually initially people were very scared of this, right? Saying, okay, well, what if I initialize here and I do gradient descent, I end up here, right? At this local minimum, right? But I would like to get here, right? So previously I never had to worry about this. I just start here, I do gradient descent, and I always end up at the minimum, right? Here there's many minima, right? So in fact, you could also have a saddle point, right? You could have something like this, and you could end up here, right? Because there's also no gradient. So you get very, and someone said, saying we need the global minimum. Actually, we don't. We just need something that has a very low loss, right? But what we don't want is to get stuck here, which is a pretty bad minimum, right? Like the loss is very high here, right? And if we can actually end up here, right? So with a neural network, we basically learn something, and we're never quite sure if we could have done better, right? But we would like to avoid getting trapped in very bad minimum. One trick is just to initialize it randomly a couple of times and see, where you end up, right? And basically take the one that has lowest loss. So it turns out there's actually a very easy trick. And this trick is a really old trick that people just didn't take seriously. And that's called stochastic gradient descent. And so stochastic gradient descent does the following. Remember in gradient descent, we said, our parameters, let's call them theta, becomes theta minus alpha times the gradient of the loss with respect to our parameters, right? We did this last lecture, right? But what is the gradient with respect to loss? The gradient with respect to loss is the following: is the sum over all our data points, the gradient of every single data point, right? So let me just L of h of xi comma yi. Okay, this is the thumbs up if you're with me. Okay, good. Well, all right, so we compute gradient descent, and so the gradient is really just a function. It's basically just decomposed over every single data point, right? And let's we average this because the loss can be the average. Then actually what this really is actually just the expected loss, right? If you take a random data point, the expected gradient of h of xj comma sigma yj. And so what you can actually do is, instead of computing the full gradient, you just pick a random data point and just take a gradient step with respect to that data point. That seems like a crazy idea, right? So you want to minimize this function, right? And the gradient tells you go in this direction, right? But you're not actually using the gradient. You're just approximating the gradient. You're just taking one data point and say, oh, for this data point, you should go to the right or you should go to the left or something. You know, basically kind of, it's a little like a drunk man, right? You basically just take a really bad approximation of your gradient and go down that, you know, follow that. But what people realize is, because that is so noisy, right? It's what actually happens is that you don't get trapped in these local minima. These local minima that are kind of really bad, you have to be very precise to find them, right? So if you actually use a very imprecise optimization algorithm, you kind of go past them. And you know, these global minima, or essentially, you always get trapped in those, right? Because there's nothing deeper, right? So you know, at the end of the day, you will get stuck there, even with a really, really bad algorithm. So that's called stochastic gradient descent. So basically, for every single gradient step, you ignore almost all of your data. You just take some little random data and pretend that's all you have, and just take a little gradient step and optimize it. and if you use that trick, you can actually learn these neural networks really, really well. Okay, let me just see. We have 8 more minutes. I want to show you a little demo. Are there any questions at this point? What are the global minima is not different from a local minima. And so actually the way it works is there will be many such minima that are kind of all roughly the same, in fact exponentially many, and which one you exactly get stuck in is not a big deal, right? But if you have one that's kind of, well, what you want to avoid is a minima that basically where the function is only this shape just because of this very specific training data you have. Right? And if you had different training data, actually that wouldn't be a minima at all, and you wouldn't get stuck in it. And essentially with stochastic gradient descent, that's what you're doing. You basically, by sampling some data, you basically say, well, if for most of your data, this is actually not a good position, then actually you will go past it. Does that make sense? Any more questions? Just to make sure I got the deep learning case, the matrices in the hidden layers are random matrices. That's exactly right. So these matrices W, U, V are initially random, and then you do gradient descent and take gradient with respect to all of them, right? Each time you take a gradient step, you update them. Okay, my understanding of optimization is high-dimensional optimization problems have few local minima. Does it apply to neural networks? Yes, it does. So essentially, there are many local minima, but there's so many different directions, right? That it's very easy to get around them, right? And so stochastic gradient, and so the problem essentially was that what happened, machine learning people went to experts in mathematical optimization, and they came up with these really good algorithms to minimize functions. And these algorithms like LBFGS or conjugate gradient, and I don't know if you're familiar with them. They're kind of like heat-seeking missiles, right? They basically find the local minima, right, with amazing precision and really, really fast, right? And so for a long time, machine learning community thought we have to use these kind of algorithms because that's what people use in mathematical optimization. And then once people started switching to stochastic gradient descent, they realized, oh, it's actually really easy to avoid these local minima because, in this high-dimensional space, there's so many ways around them. Okay, the question of deep multiple layers versus a wide layer is the practical one. It's more efficient to train. So in practice, if you have deeper networks, you often need a lot less data, actually. But theoretically, you could approximate any deep neural network with a single hidden layer neural network. But in practice, it's much more efficient to have a few layers often. The minimums are the features that are not as important of a of a feature that minimizes the loss. The minimums are the features that are not as important. No, the minimums are basically configurations of these matrices. They're basically parameters that basically, you know, if you change them a little bit, you do worse, right? But if you change them a lot, you can do a lot better, right? That's basically what it means. And so doing better means getting lower error on your training data set. Does that make sense? So you basically try to learn these parameters to make as few mistakes as possible on your training data set, or to fit the line as well as possible. But you're kind of a little bit stuck, right? And you have to kind of move the, you have to move, you know, you basically have these points, you approximate them with a line. And so maybe you have to move the line a whole lot to actually get a better approximation, right? So that's a local minima is basically something where a small change actually makes it briefly worse, but then actually you get better. All right, let me quickly show you a demo that is really, really cool. And this demo actually comes from, it's actually, sorry, I made a demo for a talk I gave. And can you see my screen? Oh, yeah. And, but I couldn't find it anymore. And so I just realized that Paul Ginsberg, that some of you may know, he actually was inspired by this for his class and actually made an even better demo. And so I just found it on his class webpage. And so because I lost my own demo, I'm now using his. So thanks, Paul, for saving me here. And so let me just, you know, I'm basically adding a few data points here. And so I'm trying to approximate these data points in a regression problem. And you can see at this point, right, the linear, what you see, the blue line here is a linear fit. And that's pretty bad, right? And so let's do a neural network and with one hidden layer. And so let's see what happens when I, for example, add, you know, 2 nodes as a hidden layer, right? And so now basically I have my input, my output, and I have 2 nodes, right? And what you basically get is you get 2 kinks. So you have your function, then you have your first kink, so now you have another linear function. Then you have a second kink, you have the third linear function. Okay, does that make sense? So these 2 hidden layers basically now allow me to approximate this data with a piecewise linear function with 2 kinks, right? You can now say, oh, that's all right, right? But maybe I should do it a little better. So let me maybe add 3 kinks, right? And so now you can see, all right, it's doing better, right? So now, you know, actually in this case, well, the kinks are kind of outside the screen here. And so, you know, you can see the higher I go, the more complex this function gets, right? So here's like 1, 2, 3, 3 visible kinks here right now, right? And so in the limit, I could actually go to 20. Right? And so now actually becomes a really, really good approximation of this function. You can see all these little kinks, they don't do a whole lot, right? But they kind of make it kind of somewhat smoother, right? And so I'm approximating this data set. Maybe I can do something to make sure Andrew is talking after me, but maybe I can do something, data set that's maybe a little bit more challenging. So here, okay, good. If I now have maybe 3 kinks, you know, see, that's not enough, right? But let me add 20 kinks. So I had 20 hidden nodes. You can actually see now I can approximate this function really, really well, right? And I don't know if there's any questions about this demo. Actually, I don't think I can see. I cannot see the questions right now.
One question: with 20 neurons, are you starting to overfit?
Ah, very good point. So overfitting is basically, yeah. So you know, let me, you know, let's see if you can over. I don't know how you can do 100. You can see actually generalizes surprisingly well. The interesting thing about neural networks is that even if you have many hidden neurons, because we use stochastic gradient descent, the way the optimization works, actually, you don't use all the parameters if you need them, if you don't need them. So basically, I'm changing the parameters very little every single time. So they are surprisingly robust against overfitting, actually. And I don't think we have time to go into this today. But essentially, think about it that I'm just allowing to kind of, I'm changing it so little every single time, right? That basically there are some solutions that would be crazy, like, but I won't get there for a long time. So usually I stop my optimization before I reach those. And so the one thing that why people like neural networks so much is because actually you don't have to worry about this too much. You can make a really big neural network, and in practice, actually, it works surprisingly well at functional approximation, and it tends to not overfit, actually. Very good question, though. Any more questions?
I think maybe one more question. So in the case of a redundancy, the kink dots would overlap in your animation? Would there be multiple kinks like on top of each other, near top of each other?
Yeah, you basically see this, right? So here, these kinks, I mean, the question is, do you really need all of these three? Probably not, right? So here it does this very, very smoothly. Well, it's just trying to be fancy here, right? They're probably not quite required, right? And so that's essentially what it does, right? It basically breaks a few more times than necessary. Not a big deal, right? That's essentially what's happening here.
Great. Wow. Thank you. So,
Andrew.
so now
right,
we're going to switch over to our next lecturer, Andrew Wilson. So Andrew Wilson at NYU is also going to give a 3-lecture series, and Andrew and Kilian coordinated the contents of lecture so that they will be complementary, I believe. And I hope everyone can continue engaging with the lecture through the chat window. Go ahead, Andrew.
Thanks. Well, it's really great to be here and nice to meet everyone virtually. So I'm at NYU. I'm a professor in machine learning. I was previously at Cornell, where I met Yuna and Kilian and many others, and started a number of exciting collaborations. Before that, I was actually a physicist. So I do have sort of a physics perspective on a lot of machine learning, and I'll try to bring some of that to the lecture today. And in fact, I entered machine learning without really knowing very much about it. And before, it was a very hot field. And so a lot of this will be what I would tell myself if I could kind of build a time machine and go back, a decade and say a few things that might save me a lot of kind of effort and frustration. And in that vein, a lot of what I'm going to describe isn't easily found in textbooks. So when I started thinking about machine learning, there appeared to be a lot of contradictory conventional wisdom. So in the sort of front lines of ML research, I found that people were very excited about building huge flexible models. So Kilian has talked about big neural networks. Sometimes these neural networks have even more parameters than data points. And I'd actually joined a group that was excited about an area of ML called non-parametrics, where in fact you have an infinite number of parameters. But then if you looked at what people were doing in other disciplines like econometrics and so on, often there was a very different emphasis. People valued things like parsimony, having as few parameters as possible, having very simple interpretable models, being very careful to avoid overfitting, et cetera. So it felt like there was some sort of contradiction. What is it? Or do we want a model as big as a house, or do we want something very simple and interpretable and manageable that won't overfit? And in fact, the answer really is kind of both. And the way in which they don't contradict each other is basically by understanding the generalization properties of the models we build as having to do with more than just flexibility. It's more of at least a two-dimensional concept where we're thinking about the expressivity of these models, but also this other thing called inductive biases. What types of solutions do these models like to find? And this is also at the heart of understanding why approaches like deep neural networks can work really well. Also, most of my lectures this week will really have a probabilistic flavor. And I find that the probabilistic formulation really helps us unify a lot of different topics that seem quite disconnected typically in machine learning. Sometimes when people first start sort of learning about AI, it seems like we just have like a grab bag of a bunch of methods and they're kind of disconnected and it's kind of random and you have to memorize sort of supervised, unsupervised, semi-supervised. Here are the methods that we use for each of these domains. Here are a few algorithms, and it all just seems like kind of kind of arbitrary in a way. In fact, a lot of this material is really deeply unified through probability theory. And by understanding how everything connects together, we're also much more well equipped to build our own methods that are tailored to a particular problem of interest. So it's all good to learn about neural nets and logistic regression, et cetera. But of course, we'd wonder, well, how did people come up with those models in the first place? Let's say I wanted to propose a whole new model class that really makes sense for the problem that I'm considering. How would I even approach that? And so this is what the probabilistic sort of perspective really helps us do. It helps us both think about how we should be constructing models, but also how we should be constructing training objectives, how we should be teaching these models, and how we can actually view a lot of different procedures, both in supervised and unsupervised learning, which we'll be discussing on Friday, and see them essentially as following the same kind of mechanical procedure. All right. So let's start with a simple pattern recognition problem. So let's suppose we have some data points. We can imagine that there are, for instance, CO2 concentrations, and our horizontal axis represents time. So we're measuring CO2 as a function of time. And maybe it looks a little bit like this. And the question is, let's suppose we want to build a model to fit these data and make predictions into the future. So suppose this goes up to 2021, and we want to know, what are the CO2 concentrations going to be for the next couple of years. And we're going to be considering 3 different model classes. Choice 1, y is just a linear function. Choice 2, y is a cubic polynomial. And choice 3, y is a 10,000th order polynomial. Let's just take a vote in the chat. Type 1, 2, or 3, corresponding to the choice that you would make to fit these data. Don't think about it too much, just kind of react. Okay, very interesting. So definitely 1 wins by a pretty large margin. And there are a couple 2s and 3s, and actually more 3s than I expected. So almost no one chooses 3 because they're scared of overfitting. And in fact, classical statistics would say, well, why would you use this model with more parameters and data points? But I just said in a way that we're already using neural nets that often do have more parameters than data points, and finding we achieve very good generalization as a result. And Kilian gave some intuition for that. From an optimization perspective, where if we're navigating this really high dimensional space, maybe there are more ways we could avoid kind of bad local optima, et cetera. And in fact, in this lecture, I'm going to argue that we would want to make choice 3. And in fact, choice 3 is probably insufficiently expressive, insufficiently flexible, because we know that there's some setting of the parameters in choice 3, the WIs, which should be able to give us a better solution than could possibly be managed by choices 1 or 2, which are just special cases of choice 3. And in fact, in this vein, we actually would want a model which is even more flexible, maybe with 1 million parameters, or if we could imagine it, infinitely many parameters, so that we could have our best possible chance of discovering a good solution to our problem. And in fact, we are seeing this kind of trend. Models are getting bigger and bigger, and we're often seeing better and better generalization. Now, but what about overfitting? So it is possible to sort of have a setting of parameters that will enable us to run through these data points perfectly, but not provide very good generalization. And the key to kind of overcoming that obstacle is really understanding this distinction between flexibility and what are called inductive biases, which will be a key topic of this lecture, and being very careful not to conflate flexibility with model complexity. So quite often these two things are talked about interchangeably, when in fact they're very different. We can have very expressive model classes that in some ways are not complex at all. And we'll sort of discuss what we mean by that in a moment. But let's just, for the time being, forget everything that we may know about machine learning or statistics and go back to high school and just imagine how we might approach trying to fit these data points that I've drawn at the top here. So what kind of mechanical procedure might we follow? And feel free to unmute if you like. If it gets a bit hard to manage, we can kind of go back to chat, but just think about it for a minute and then tell me, how you would approach fitting these data points. So if I'm telling you, here are the data up to 2021, and I'd like to make a prediction up to 2025, what step-by-step procedure would you follow? And you're not allowed to use anything that you've learned about machine learning or statistics. We're going right back to high school. Maybe we know calculus, we know trigonometry, we might know a little bit about optimization. What would you do? And there are many right answers to this, so don't be shy. So I'll call on you in maybe 30 seconds or so. Splines, did you really know about splines in high school? I mean, maybe you're very precocious. Just fit to line and plug in desired year. Right, but just sort of mechanically, what would you do? Guess and check, like what step-by-step procedure would we follow? So I'll give you a hint, like, okay, draw a line with a ruler, manually calculate slope and intercept. That could be one reasonable approach. If we went beyond that, what might we do? So we know about a few different function classes. We know about linear functions, we know about polynomials, we know about trigonometric functions. So we would probably start, if we weren't just eyeballing it and kind of drawing a straight line flit, we would start by just specifying some kind of function. Some function, f of x, with some parameters, w, to fit the data. For example, e.g., f of x w equals w naught plus w1x plus w2 x squared plus w3 x cubed. Maybe we would see some quasi-periodicity in the data, so we might want to throw in like a cosine term or something like that with that would account for seasonal variations, things like this. Maybe there would be some parameters there too, but basically we would look at the data, try to choose a functional form that appears to be a reasonable description of the data, and then we would have these parameters, the w0, w1, w2, w3. So what we would do next? How would we estimate? How might we estimate those parameters? Derivative 0, but maybe we have to go back a step. Like, what are we going to use to try to say these are good parameters or these are bad parameters? L2 norm. Let's not use jargon. Let's kind of just go back to high school. Least square fitting. Did we know about least square fitting? Plug in a few values and solve for the parameters, but we still need to go back a step. Like people are talking about taking derivatives and things like this. Taking derivatives of what? Error between data and fit. Okay, great. And what might that be? Distance, but what distance? There are many ways we could take distance. Mean square. So that could be one example. So let's specify a training loss. For example, loss as a function of W equals the sum of the data points that we observe minus the outputs of our function at the inputs, the xi's that correspond to those data points. So this is sum xi squared, and we sum over the n points that we've observed. So we see n data points in this instance. This is an example of a loss function. What we're saying is how far away are the outputs of our function f of xw that we've chosen from the actual data points. And we have some free parameters that we want to estimate, the w's. We're going to estimate those by trying to minimize that difference. Now, why choose squared loss? Why not like absolute value or something else? Like, why not take this to the power of 10 or do something completely different? It seems like there are many possible loss functions we could specify. Why choose squared loss? Connected to normal distribution. Okay. Easiest differentiable. It's kind of convenient. Absolute value is not analytic. But we could take it to the power of 4, for instance, or do something a bit different. Or there are ways that we might sort of still be able to maximize something like the absolute value. What would be a difference between, say, the squared loss and the absolute value loss? Like, how might they behave differently in trying to choose these parameters W? Right, so the squared loss is going to be heavily penalizing big discrepancies between the yi's and the f of xi's. An absolute loss wouldn't do this as much. And so we can see that there are some different properties, like the loss functions that we specify will have an effect on the functions f of x that we learn, especially if the function is not capable of fitting the yi's perfectly. And so this is kind of an important design decision, and one that we shouldn't necessarily sweep under the rug, even though quite often we do make sort of standard assumptions and just say, okay, we're doing squared loss and this is what we do. If we did sort of average squared loss in this case, it would be the same, because just multiplying this sum by 1 over n wouldn't change the w that minimizes this function. Okay, so that's what we've got there. And then once we have that, we want to minimize, find the w hat, which is the argmin over w of f of, L w, and then make predictions. So we've got our function now, and we've got our parameters w hat. For any x. All right, so that would be kind of like a procedure that we could probably come up with just with basic high school math. Although there are a lot of decisions to make here that will have a pretty big impact on the performance of our approach. So which functional form do we choose? What's the training loss? In some cases, even what procedure are we going to use to optimize this training loss? In some cases, we might be able to get an analytic solution. In other cases, there might be no closed form solution for the W that minimizes our training loss. And so we need to use something like gradient descent or stochastic gradient descent. And all of these things might kind of affect our performance. And in fact, this approach that I've laid out is prone to overfitting. So if I make F really, really flexible, it's quite possible to find an f of xw, find a w such that f of xw fits all the yi's perfectly, but then makes kind of crazy predictions. because there's nothing in here that sort of says, okay, we have to kind of have a nice looking function that reflects kind of the trends that we kind of believe to be kind of important in the data, rather than just, anything that just sort of runs through all of these points perfectly. So we would probably want something, a fit that looks, maybe like this, rather than something that maybe runs through all the points perfectly, but is kind of, crazy, and then just does something kind of weird when we move outside of the data. And this loss function doesn't really help us avoid those types of solutions. So sometimes something that people do is called regularization to try to mitigate this overfitting effect. So we introduce a complexity penalty to discourage finding solutions that don't generalize. That is, solutions that don't make reasonable predictions outside of the data points that we're observing. And so a common regularizer is L2 regularization, where we penalize the norm of our parameters. So we have our loss, and we create a new loss, which is LW plus W transpose W, where I've collected all of my parameters into some vector W. So W vector is just W naught up to WD if I've got D parameters. And so basically this just says, let's not use big weights. And you might be thinking, well, that seems kind of, where does that come from? Why are big weights bad? If we think about models like polynomials, large weights will often correspond to big oscillations. And so we'll probably want to discourage those. But if you were thinking this seems kind of arbitrary, you're right. Of course, whatever complexity penalty we have should depend a lot on the functional form of the model we're using. So for example, if I had used something like a polynomial, but then I had changed the parameterization such that I'm using 1 over the weights rather than just the weights, then in that case, small weights would be probably a bad thing that would also lead to kind of overfitting. So whether we want big or small parameters, for instance, would totally depend on the functional form of the model we're using. There's also a question of like, how much do we want to penalize complexity? So that's determined through things like this hyperparameter lambda, which we can't learn in a normal way. Can someone tell me why? Like, let's suppose this is our new loss function, which I'll call L tilde W. Can someone tell me why, it also depends on lambda now as well, why I could not minimize L tilde with respect to lambda and get something reasonable? Let's just think about the objective that we're trying to minimize. Just looking at it there, what value of lambda would give us the minimum value? 0, right? So we would always just set this thing equal to 0. And so that's not going to be helpful. So we then need to use a procedure, for example, called cross-validation, which requires us to kind of separate out some of our training points to have this special sort of validation set. And then we consider a bunch of different settings of lambda, like lambda equals 0, 1, 2, 3, 4, whatever we think might be reasonable. And of course, that's going to be a hard question in itself. Then we'll retrain our model with each of those different values of lambda. And then we'll go and see which model makes the best predictions on our withheld data points. So this kind of special validation set that we've created, and Kilian may have discussed a procedure like this. The problem with this, though, of course, is how do we choose our validation set? And what if we don't have very many data points? Maybe it's kind of tedious to sort of, or problematic to remove the data points we do have because we want to use as much information as possible to specify our function, f of xw. And what if we had many regularization parameters? Suppose it wasn't just lambda, but maybe we actually want to penalize different weights differently. So maybe some of them we want to pay a larger penalty for being big, others we want to pay a different sort of penalty, etc. Then this kind of procedure suffers from what's called a curse of dimensionality, because if we're doing something like grid search, saying, okay, we want to consider lambda equals 0, 1, 2, 3, 4, etc., and we have a bunch of different lambdas, we can see the number of hyperparameters that we need to check is going to grow exponentially with the number of sort of regularization parameters that we have, the number of values we need to check. And so this is kind of like an intractable procedure in general, and requires us to make a bunch of other ad hoc design decisions. So the point that I'm really trying to make here is that a lot of the decisions that we're making in kind of standard statistical modeling and machine learning actually feel a bit arbitrary, and they're really going to affect our final answer. So this kind of begs the question of whether there's a better way to understand this process. Can we think of a more kind of first principles approach to deriving various loss functions, to proposing various regularization procedures, to avoiding the need to do things like cross-validation in the first place, to specifying functions which will be expressive because we believe the real world is kind of a complicated place, but also won't suffer from overfitting. How do we do all of that? And so this is where probability comes in. So the first step when we are following a probabilistic approach is to specify what's called an observation model, which is kind of a story that relates our model to the data points that we're seeing, and it depends on some sort of probability distribution. So step one would be formulate observation model, and if we're thinking about regression, we could say, for instance, that the points that we observe, y of x, are equal to some latent function that we don't observe, the kind of ground truth, plus, for instance, Gaussian noise. So here I'm saying epsilon of x comes from a normal distribution with a mean of 0 and a variance sigma squared. Of course, I could have said something different, and we'll get into that in a moment. But this is just an example of an observation model which says this is how we create our y's from our x's and the parameters that we have. Okay. The next step is create a likelihood. The likelihood is the probability that we would generate our data set using that observation model. So the likelihood is so let's say we have a data set. Maybe let's put this up here. We have a data set D, which is our xi, yi pairs in this instance. What we want to do is find what is the probability of the data given the parameters that we're trying to estimate. So someone's asked a question, is f of x w the polynomial function as in the previous slide? So it's really any function that we want. Right now I'm trying to keep things fairly abstract and general, but it could be the polynomial. So we could imagine that it is the polynomial that we're trying to fit. But it could also be a neural network if we like. It could be a trigonometric function. It could really be just any kind of generic f of xw, some function that has some parameters that we're trying to learn. It's a good question. Okay, so we want to create a likelihood. So how do we do that? So P of D given W and sigma squared. So if we assume that our data points are drawn from this observation model in equation 1, and that when we condition on our parameters W and the noise of our observations sigma, that these data points are independent, then we can just write down this likelihood as a product from I equals 1 to n of Gaussian distributions, and the mean. So this is going to be for each y of xi, which I'll just say is yi for short. And the mean is going to be f of xi w, and the variance is going to be sigma squared. Now you might be wondering where I got that. That basically comes from the fact that equation 1 can be equivalently expressed as saying that the distribution of y for each x given w and sigma squared equals n, and the mean is going to be Gaussian and the variance is sigma squared. The reason we know that is if we look at equation 1, we see that we've got some function f of xw, and that's not random. There's nothing random about that. So it's just like a constant plus some random variable epsilon, and we say that's a normal distribution. And so a normal distribution plus a constant is going to still be a normal distribution, and its mean is going to be shifted by that constant. And in this case, the constant is f of xw. And I say constant not because f of xw doesn't change. Of course, it depends on x, but it's not a random variable. Okay, so that's how we get our likelihood function. Any questions about that? About how we reached our likelihood function? And if you're confused, please say so. If you understand, say so too. Maybe press 1 if it all makes sense right now. Or raise your hand or whatever on Zoom. Okay. Looks like people are following. If you're not, definitely speak up, because these are the foundations and they'll be important for a lot of the other material we'll be discussing. Okay, so here's our likelihood. Now I'm going to ask you a question. Let's suppose we want to maximize our likelihood to find W hat equals argmax over W P D given W sigma squared. How will our solution relate to what we find if we follow the previous approach of minimizing a loss? So just take a minute, think about this, maybe try to expand equation 2 a little bit and see if that can help you answer this question. Can you explain why n in point 2 has 3 parameters? Right, so this is just a notational thing. So that's saying that this is a Gaussian, also known as a normal distribution, and it's Gaussian in y. So the random variables are the yi's, the different data points that we observe. And the mean of that Gaussian is f of xi, and the variance of that Gaussian is sigma squared. And so sometimes people write normal distributions with just 2 parameters, the mean and the variance. Here, before the semicolon, I'm also just being very explicit in saying that the random variables or the different yi's? It's a good question. No worries. Product of Gaussians is a Gaussian where the argument is a sum. So maybe I'll phrase the question a little bit differently to make it easier to communicate an answer. Will the solution that we find following this approach be the same or different than minimizing squared loss like we were considering before? 1 for the same, 2 for different. All right, everyone's saying it's the same, which is good news in this case. So let's actually just unpack what the likelihood, let's derive that it'll be the same. P of W, sigma squared, is this product from I equals 1 to n of P of yi given W sigma squared. And in that case, we have n yi f of xi w sigma squared. And we can unpack that. So these are just Gaussian densities. So this is going to be 1 to n, 1 over the square root of 2 pi sigma squared times exp of minus 1 over 2 sigma squared, f of xi w minus yi squared. So we've got this product. Now, if we are just concerned with finding the W that maximizes this expression, we can take a log and consider maximizing that because the log is a monotonic transformation and it won't change our solution. So the log likelihood is going to then equal, this product will turn into a sum. And so we're going to get minus 1 over 2 sigma squared times the sum from I equals 1 to n of yi minus f of xi w squared minus n over 2 log 2 pi sigma squared. Okay, so now let's consider the negative log. That's just 1 over 2 sigma squared. Okay, well, maybe let's not write all that out. That's a lot of work for something that's kind of easy to see. Okay, so here is our log likelihood. If we take the negative of this and we just care about finding the W that minimizes the resulting expression, we see that we're going to just get the same answer as we got when we specified squared loss. The sigmas don't depend on W, so they're not really going to change anything. And so one might ask, well, what do we gain by following this approach instead of just saying, let's use squared loss? So the important thing that we gain from doing this is a mechanism to actually construct a loss function that might actually be very well suited to the problem that we're considering. So we're not just pulling squared loss out of thin air anymore. We see that it directly corresponds to the assumption of Gaussian noise on our observations. Now, let's suppose instead that we assumed that our observations had outliers. So maybe our instrument that we're using for taking measurements or whatever it might be is prone to sometimes making very big mistakes. Then we might actually want to choose a different noise distribution. So for instance, if we had specified our epsilon of x as coming from what's called a Laplace distribution, then we would get the absolute value loss function. If we had used a t distribution for our noise, we would get a different loss function still. And so the choice of loss or choice of noise distribution corresponds to the loss function. So, for example, Gaussian noise squared loss. Laplace noise, absolute value loss. The really cool thing about this is we can also derive all sorts of loss functions that are not standard, but might make a lot of sense given our problem at hand. And the idea is we probably have more basic intuitions about what kind of noise our data might have, or more generally, what sort of observation model we want to use to relate the data points to the function that we're trying to estimate, than what we would get if we were just to kind of immediately try to specify a loss. So although maybe things like the squared loss seem kind of intuitive and obvious, and that's why it's kind of a good example to start with, if we're doing something like classification, and I saw a question at the end of Kilian's lecture on neural nets, well, how do we predict class labels? This sort of makes sense for regression. There's a different loss function that people often use for classification called the cross entropy loss. There's no way that we would just be able to kind of specify that from the start, or it would be very unusual to kind of say, okay, well, that's the loss function we want to use for classification. But it's very, very, very easy to derive that loss function using a probabilistic observation model that goes from some function we're trying to estimate to the probability of a class label. And we'll see that in a moment. So this is a very flexible, powerful formulation that'll help us create a loss function for any problem that we want to solve, especially if we're going beyond the simple setting of doing kind of regression, and maybe something like squared loss might be kind of reasonable. Okay, so what about the regularizer? Where does that come from? Now, let's suppose instead of maximizing a likelihood, we're thinking about maximizing a posterior over parameters. So suppose instead of finding argmax over W, P of D given W, we instead want argmax over W, P of W given D. And in a way, that's probably more what we would be interested in. So this is kind of sometimes a subtle difference, but it's kind of at the heart of a lot of seeming paradoxes in probability involving Bayes' rule, etc. Quite often we're more interested in conditioning on data and finding some parameters than the other way around. So this is saying, well, what is the most likely setting of parameters given the data set that we've observed? And I think that's really kind of more the question that we want to answer. And let's see how these two things relate. So that is going to equal, so let's just say, what is P of W given D? So using Bayes' rule, that's going to equal P of D given W, P of W over P of D. So this is just Bayes' rule. Now, let's take the log of this thing, because as we saw, taking logs doesn't really affect our answer if we're doing optimization. So that's going to equal log of P of D given W plus log P of W minus log P of D. Okay, so log P of D does not depend on the parameters we're trying to estimate. So let's just kind of forget about it for a moment. We can see then that this log likelihood corresponds to our loss. And this log prior, the log of P of our parameters W, but not conditioning on anything, corresponds to our regularizer. For instance, if we say that our prior belief before we observe any data about W is that it comes from a normal distribution and it's got some mean 0 and some variance, let's say alpha squared I. The reason I'm saying identity here is this is like we have many parameters W. So it's a multivariate normal distribution. then log p of w will be proportional to minus w transpose w over alpha squared. And so we see that we recover L2 regularization from that assumption about the parameters w before we observe data. And so this sort of provides us with a mechanism now of proposing any regularizer that we like. If we have some sort of prior belief, or even the lack of a prior belief about w, we can create a regularizer that expresses that belief and enables us to balance complexity in a reasonable way. And so that's where all of these regularizers come from. And here's kind of a recipe for creating our own regularizer for a particular problem. Like, let's suppose, for instance, that we're considering a very well-defined physics problem where we do actually have prior beliefs about what these parameters should be. Like maybe that the prior expectation isn't 0, it's something else. Then we can write down that distribution and use that as a regularizer in our problem. One other advantage to this formulation is we can also estimate things like noise. So on the last slide, we had this expression that we were considering to try to find our parameters w. If we believe our model, f of x w is kind of reasonable with the right setting of w, then we can also optimize this expression with respect to sigma and find some reasonable estimate for what the noise might be in our data set. Okay. However, this is not a fully Bayesian approach that I've described here. And there still are a number of design decisions to make, like, how are we supposed to specify alpha, for instance, in this prior over W? What would be a reasonable alpha? And would that procedure involve something a lot like cross-validation? And if we just kind of stuck with what we're doing here, then the answer would be yes, we would have to do something like validation to learn alpha. Maybe at least we have an interpretation of where this regularizer comes from. But some of the mechanics involved in trying to learn W, specify alpha, and so on would be very similar, once we've written down the loss function that we want to minimize. So we'll now discuss like a completely different paradigm for trying to make predictions. But before we do that, maybe let's take a break for a minute for questions. So does anyone have any questions about anything that I've said or written down so far? Can you clarify how you would approach it if I knew absolutely nothing about W? So if you knew absolutely nothing about W, then I think you would want to express that in your prior. So you would want to say, I have uncertainty about what value this parameter should take. And if we were using something like a normal prior, then that would correspond to having a very large alpha. And I'll argue, especially when we follow a fully Bayesian approach, that this will be very meaningfully different from having no prior at all. So this is actually a confusion that a lot of people have. And right now there isn't sort of a way to resolve the confusion until I talk about fully Bayesian methods. But it stems from this connection between what's called maximum a posteriori estimation, which is what I'm describing on this page here, and regularized optimization. So let's suppose I made alpha really, really, really big, then that starts to look like a uniform distribution. And so it stops kind of depending on W. And so if we optimize that, that's like having no prior at all. And so one might say, well, if we really know nothing about our parameters, let's not worry about priors. And that would be true if we were talking about regularized optimization. It's not true if we talk about Bayesian methods. So while we only have about 10 more minutes, we're going to see a load of examples at the beginning of the next lecture where you see big differences actually between the Bayesian approach and the regularized maximum likelihood approach, even if you have uniform priors. And I think after you see those examples, you'll never want to use a non-Bayesian method again, because it really just doesn't make sense. It's actually kind of crazy. And I would contend that that many non-Bayesian methods work by virtue of being kind of an approximation to the kind of proper kind of Bayesian procedure. What if our problem follows negative probability instead? Negative probability, I guess, isn't a very well-defined concept. So there's an interesting Feynman article on negative probability, but it's more of a kind of speculative thing. Maybe is there something in particular that you had in mind? Okay. Yeah, I mean, it's something fun to think about, but in general, negative probability isn't really something that comes up much. Is there an intuitive reason one would want to minimize instead of t? Both intuitively look like a good candidate for a cost function. Right. So the reason I would say that w given d is a more natural cost function than d given w is because we are given our data d, and we do want to know what is the most likely setting of parameters given the data that we've observed so far. And that should include any kind of prior beliefs we have about those parameters, even if our prior beliefs are ignorance. Whereas d given w is like, what is the w that maximizes the likelihood of d? It's not in this sense quite what we want, because it would completely ignore any kind of beliefs, or not even just beliefs, but kind of information that we have about what w might be. So I think sometimes there's this confusion also, and this is a bit of a side comment, that the parameters w ought to, the prior over parameters w ought not to depend on data in any way. That's not really quite true. They just shouldn't depend on the same data set that our likelihood depends on. So let's suppose we've performed a bunch of other experiments involving this model, involving a number of similar data sets. It's perfectly reasonable to use those data sets to specify a prior over w, and then apply that prior in conjunction with a new data set to form a likelihood. So the short answer is d given w just kind of ignores any information we might have about w, and in some cases that's a very unreasonable thing to do. Okay, now let's talk about the Bayesian approach. So the Bayesian approach is actually very simple and intuitive, and all you really need to know to deploy a Bayesian method in your work are two simple rules of probability: the sum rule, which says the marginal distribution over some variable a can be found by taking a joint distribution over, say, a and b and summing out b. If we're talking about a continuous distribution, and that's really what we've been talking about in this running regression example, then so this would be for discrete. For continuous, then we would have equals the integral of PAB integrating out B. And the product rule, which says that the joint distribution over A and B equals P of A given B times P of B, which equals P of B given A, P of A. And in fact, we can derive Bayes' rule from the product rule. So Bayes' rule isn't even really a fundamental rule. It's just a direct consequence of the product rule. So if I just actually just take the second line here of the product rule, that means that P of B given A equals P of AB over PA, which equals P of A given B, PB over PA. And so this is just Bayes' rule. Okay, so that's all we need to know to be Bayesian. Being Bayesian is just a simple consequence of following the sum and product rules of probability. And so let's see an example of that. So if we want to be Bayesian and we want to make predictions, what we're trying to do is say, well, what is the value of our target y given any arbitrary input x star and our data? That's the question we're trying to answer. And so in this regression example, just using the sum and product rules of probability, that's going to equal the joint distribution of our observations and our target variable and our parameters w given x star and d dw. So this is just the sum rule. And then this will equal the integral of p of y given w x star. Now, it turns out that if we condition on our parameters, typically we don't need to condition on our data anymore. And you can see that if you just look at these observation models that we've specified. So f of x w depends on w. If we know what w is, then we don't need the data. We use the data to try to learn what w is. So I could write conditioned on data as well, but it's superfluous. In this instance, there's a conditional independence if we know what the parameters w are, times the posterior over the parameters given data dw. So this is the product rule. And this here is called a Bayesian model average. And it's very important. So what it's saying is, rather than use just a single setting of the parameters w in this functional form that we've specified, what we really want to do is use every possible setting of the parameters to make predictions, and then weight those by their posterior probabilities. So I can explain kind of the difference with the diagram here. So let's suppose we have some data points that look like this. And you're imagining, what are the possible functions that are consistent with these data points? So we might have something that looks like this. We might have another function that looks like this. We might have another function that looks like this. And these are all reasonable explanations for the data, given what we've observed so far. And so in this sense, it's very ad hoc just to say, well, let's bet everything on just one of these functions and use that to make predictions, because it's ignoring uncertainty about what other reasonable explanations we could have for what we're observing. And so that type of uncertainty, there's kind of a jargony name for it, and it's very specific to Bayesian modeling, is called epistemic uncertainty. And that's what we capture through having a distribution over our parameters w. So we could see the maximum likelihood or the regularized maximum likelihood approach as a special case of the Bayesian approach. So map or regularized maximum likelihood is a special case of the Bayesian model average if we approximate P of W given D, the posterior distribution over our parameters W, as a delta function centered on the map parameters, where W map equals argmax over W of P of W given D. So basically, we have our model that we specified. It has some parameters we'd like to estimate. We've observed some data. That data gives us some information about what those parameters should be, but it shouldn't entirely determine those parameters. And so we have this posterior distribution over our parameters W. And maybe, for example, it looks a little bit like this, given what we've observed. And the classical procedure just says, well, let's just use this point. And let's ignore the fact that there are probabilities that W could be something very different, which might correspond to these different functions that I've drawn. The Bayesian approach says, well, let's actually just use the sum and product rules of probability and find what we really want to find, this predictive distribution, which corresponds to a Bayesian model average. And when we follow this procedure, we find that we don't observe things like overfitting. We see that overfitting is actually a consequence of erroneously betting everything on the most likely hypothesis. And we'll see at the beginning of the next lecture, many intuitive examples where betting everything on the maximum likelihood hypothesis goes very, very wrong. And using a prior in conjunction with the Bayesian model average very naturally resolves these pathological behaviors that we observe, even if that prior is simply saying, I have no idea what the parameters are, it's just uniform, I don't know. Even that will give you very different predictions when we do this Bayesian model average. All right, so that's the end of the first lecture. If we have time, we can take a question. Otherwise, we can do it offline. I guess would know.
We can take questions if
there are. We've had questions throughout as well. So.
Right. Are there any pressing questions? If not, let's thank Andrew for a wonderful lecture.
Thanks, everyone. So it asks what X star is. It's just any X where you want to make a prediction. So I'm just kind of trying to separate it a little bit from the rest of the notation. But we could have written X as well. It's just wherever we want to make a prediction. So if it's regression, it could be a time or a spatial location, for instance. If it's classification, maybe we've got an image and we want to know what the class label is.